So let's now talk about something that is a talk I hoped I would not have to give. I did not plan to give until last month when I saw other talks about memory model and atomics, and I said, there's just got to be information in one place about this, including the parts we hoped never to have to teach. So over breakfast at our table, we were discussing which was more cruel to you, to inflict a deep universal references talk on you yesterday right after lunch, or to inflict a deep atomics and memory model talk on you, not only first thing in the morning when you've barely had the chance to have your first hit of coffee, but through the entire morning up till lunchtime. And we decided both were equally cruel, so here we go. This talk is not only about stud atomics, it's about the whole C++ memory model, but with a focus on stud atomics, because first I want to cover the rules that apply to all kinds of synchronization, including mutexes and condition variables and atomics. But then we'll delve specifically into atomics all the way down into the gory details of the hardware on several popular platforms and architectures to see the reasons why things are the way they are, where the hardware is today, and how it's moving in flight today. So we're going to start with defining basic things like races, optimizations, the memory model, and how those three things really go together and are important. We're then going to talk about ordering. So as Scott started speaking to in one of his review slides, what about acquire and release? What do those mean? And even if you've encountered those before, we're going to be really crisp. These are very fundamental concepts. And it turns out there's more than one kind of acquire and release, with a very slight but important difference. We're then going to talk about how this applies to all kinds of synchronization, mutexes, atomics, and fences, and how to use each one, including why you almost never want to use standalone fences. Then we're going to talk about things that this implies for compilers and hardware that you shouldn't ever need to know, but sometimes hardware and compiler have bugs, especially as they're implementing this stuff, or your program might have a race condition which exposes these things. We're going to talk about code generation performance on a slew of popular platforms, and then because this talk probably doesn't fit in half a day, if we have time, we'll talk about relaxed atomics. This is the part I hope to never, ever, ever to have to teach, but unfortunately, maybe we do. And if we get to it, a coda on what volatile means and what it's for. Just a couple of slides, which you have, but the goal is to get up to here. This is the important, most important stuff that you should be using. This is basically stuff that hopefully you shouldn't, but maybe you should, and if so, why? And then a coda. So let's start with that first section on optimizations, races, and memory model. This is the hardware that we all code for, that we would all love to code for. It's the classic von Neumann machine of a processor attached to storage. It's very easy to define the order in which things happen. I've got a thread, it does this, it writes something to RAM, look, there it goes. It loads something back, look, it fetches it from RAM, and it operates on RAM directly. Even in a multi-core world where we're no longer in a von Neumann architecture, and never will be again, we still program with the same idea that although there may be more CPU cores, we program with the idea that conceptually, they operate one at a time. Each one has direct access to the memory and reads and writes directly from global memory at a time. That's our mental model. So that even if each of these cores is running a different thread, the operations interleave. So that the end effect of your program is as if some interleaving of the operations of all your threads. Now, even the interleaving part sometimes makes people a little nervous, but it's not too bad because we protect things with critical regions, mutex lock, unlock, to make sure certain bad interleavings can't happen. And then we say, okay, those blocks somehow will interleave. And they may interleave differently from run to run. This is still the model we want to program for, but to get there, we have to make sure that we understand the memory model and obey the rules. Here is an actual piece of hardware, because here's the picture we'd like. Here's just a sample hardware, piece of hardware from 4 years ago, that what we actually program. And you see peaks and valleys. You don't directly talk to RAM, which no longer fits on this slide, to scale. It's somewhere, covering the whole next 10 floors. You have 16 meg of L3 cache. On top of that, every pair of cores on the Intel Dunnington chip shares a 3 megabyte, in this particular configuration, L2 cache. On top of that, each core individually has its own L1 cache. Oh, and importantly, a store buffer, because writes are always more expensive than reads, and so you really want to cache those and buffer those. And this is, if you squint at it just right, you'll see a mountain range of memory peaks, each with a core sitting on top. This is very far away from the model of everybody talks directly to the memory and does it one at a time. There's a lot of indirection, and a lot of memory requests can be in flight at a time. For even this complexity to be manageable, we're going to make a key assumption, which I'm going to come back to later in the talk. We're going to make the assumption that all of these caches are coherent. There have been people who are experts who have expressed the opinion that that is an assumption that is bound to fail because coherent caches don't scale. Therefore, as you get larger numbers of cores on die, that we're going to have to go away from coherent caches. This appears not to be true, and I'll point to a current reference at the end. But we're making this key assumption. Everything that I'm going to talk about in the complexity, it is merely that hard as long as we have coherent caches. And that safety net should continue. So here's the talk in one slide. You can ignore pretty much the entire rest of this talk if you simply don't write a race condition and don't use non-default relaxed atomics. In that case, your code will do what you probably think it does. So why are we having this talk? 3 reasons. First, sometimes compiler and hardware can have bugs. And when those bugs manifest, we may need to understand why and what they're doing. Second, if there's a button you want to push it, I know you do. You're advanced C++ developers. We can't help ourselves sometimes. So because there are relaxed atomics in the standard, we ask the question, what happens if I use this in combination with this? And so we're going to cover that. And sometimes you just want to have that level of control. So we're going to see why you sometimes may want to reach for those tools. So true or false, does your computer execute the program you wrote in your source code? There is a hint on the screen. No, it doesn't. Why not? Well, if you think about what we call a sequentially consistent execution of your source code, that you can take your source code and read it as text and know that the computer is actually going to do that. If it's multiple threads, that each thread will run in source code order exactly, and the result will be some interleaving. That's a very quaint concept. On Big Iron, we left that behind roughly in the 60s. On PCs, we left that behind roughly after the 80s. Because we do all sorts of optimizations and transformations. Your code, what you wrote, and especially the memory accesses, the loads and stores you wrote, don't execute in the order that you said. That would be way too slow. You didn't mean to do that. So the compiler, so don't just blame the compiler, it could be the processor hardware, or don't just blame them, it could be the cache system and the cache effect. Say, no, you didn't really want to execute that program you wrote. No, you want to execute a better program. Here, let me change it into that for you. The 2 key concepts we have to keep in mind. The first is this idea that I mentioned a minute ago, sequential consistency. So this was defined by Leslie Lamport back in 1979 as you execute your program, especially your loads and stores, your reads and writes to memory, in the order in which they would happen in a reading of the source code by the language rules. That's one definition. That would be ideal, because the program would actually do what we expect. The second key concept, which is separate, a race condition, we covered this a bit yesterday, is when you have the same memory location or object, and there's 2 threads that are not synchronized that can access it, and at least one is a writer. If they're both readers, you can read the bits all day and cache them, that's fine. But if at least one is a writer, then you can get torn writes, you can get out of order writes, you can see weird pink elephants. And we'll talk a bit more about pink elephants in a moment. So sequential consistency seems great. I mean, who wouldn't want the computer to execute the program you actually wrote? Debugging is hard enough even with the program you wrote, right? So because it can be much more expensive to do what you wrote, we may want to reorder this. And they may have even other tricks up their sleeve that you can't know about that on particular hardware architectures may do the job much better. And the common reaction to that is, excuse me, what do you mean you'll think about executing the program I wrote, or maybe run a different program for me? We'll come back to that at the end. One key thing to remember is that the only thing you care about is what you wrote in your source code and what actually happens. There's lots of space in between so that the compiler may do things like common subexpression elimination, register allocation. The processor may do prefetching, may do speculation, may overlap writes. The cache system may have store buffers, private shared caches. All sorts of things can happen, all of which have the effect of apparently reordering the memory reads and writes that your program said it was going to do. And you can't tell who did it, usually, unless you dig real deep, but you don't care. All you care about is what you wrote and what actually gets executed, and as long as this is a valid execution of that, you're good, and you don't care who rearranged it from some other valid execution that might have happened. So all we want is that the actual execution be equivalent to some sequentially consistent interleaved execution of your threads, including that every read and write appears as though you did it atomically and globally, so that one processor is using the main memory at a time. The goal is to try to maintain this illusion, because none of us want to be disillusioned. So a key thing to remember is that transformations at each of those levels are equivalent, which is really important, because it turns out that means that it doesn't matter if it's the cache effect that's doing it, it doesn't matter if the processor is doing it, or the compiler. You can reason about all of these transformations by looking at sample source code and saying, what if these lines were moved around? And in fact, memory model designers do this all the time, and they talk about memory models in terms of their effects and transformations on source code, which is good because it's something we can actually understand. So that's what we're going to follow, starting with this example. How many of you have seen Decker's algorithm or its variants like Peterson's algorithm before? Quite a few, okay. The idea here is this is in the land before locks, the land before mutexes, where we had to do synchronization ourselves. The idea here is we have two flags that let two threads stay off each other's toes getting into a critical region. You don't want both threads in the critical region at the same time, because that would be a race. Maybe one's reading, one's writing, they're both writing. So what they do is they do the following little dance. Thread 1 says, I'm going to set my flag to true. What this does, it declares my intent to enter the critical section. I haven't done it yet. I'm just declaring, hey, Buster, I want to get in. Then I look at the other thread's flag to see if he has already declared his intent to enter. If he has, I'll have to back off and try again later, do some sort of back off. But if he hasn't, then it's safe for me to go into the critical section. Why? Because he's doing the same dance. He is going to, before he goes into his critical section, he's going to set his flag to declare his intent to enter. I know that flag wasn't set before, so I'm going in. Then he sets it. I know he'll see then, when he looks over, he'll see my flag is already set, and he'll back off. So I set my flag. Then I look at his. If he hasn't set it, then it's safe for me to go in, and vice versa for thread 2. The most important word in everything I just said in describing how this works, what was it? Then. I set my flag, then I look at his flag. So what happens if you swap lines A and B? You're not going to get exclusion, right? Oh, here, let me look at his flag. It's not set. Let me set my flag and just roar right in. Well, even if the other guy isn't reordered, we'll both end up in the critical section. Sometimes, in a timing-dependent way, which is always delightful. So the way to solve this is to set flag to be some atomic type. So typically in C++11, you make it a std atomic of int, say, or of bool. In Java or .NET, you would say volatile. And then this code will work if you make those flags protected, not ordinary variables. And we'll see why this works, because if you just say, give this answer and walk away, it seems like some sort of magic incantation. It's like, okay, so it works, but it's like sacrificing a goat at midnight on a Tuesday with a full moon. It just happens to seem to work. Why does it work? And we're going to talk about that. Option 2, of course, is to write your own locks instead of re-rolling mutexes, reinventing them. Or to write a memory barrier in between some of these operations. We'll consider the various options and also why you really, really don't want to do this one, if you can help it. But let's just see how this can get you into trouble, even in a very, very strongly ordered processor that is just one step short of sequentially consistent. So remember this source code. Let's say I guarantee you an unreasonably strong execution. I guarantee you a compiler that will not reorder this at all. You do /od or something to knock the compiler over the head and say, don't touch my source code. And it says, okay, okay. And it emits object code in the order you say. Then the processor says, guess what? I'm an archaic 40-year-old processor. I will actually execute what you wrote because I'm not advanced enough to know any better. So I will execute all the loads and stores you wrote in order. So you don't have to beat him into submission because he's just archaic and he'll play along. Then the cache system, part of it is actually leaked into the processor because it deals with ordering and moving memory. I'll call it part of the cache system. It says one processor, global memory, no cache levels. But the only wrinkle I'll put in is a store buffer because writes are always more expensive than reads. This is just a fact of life, right? You can read something and cache it. Lots of people can do that independently. It requires no synchronization. But a write means you have to tell the world. There's just more work to do for a write. It has to go through more levels of cache to reach main memory, that kind of thing. So you really want to buffer writes. So imagine an unreasonably simple processor that is completely sequentially consistent, does exactly what you said in the order you said it, with the exception there's a store buffer. By the way, this is the very first thing a processor designer will put into a processor because it is one of the first most important optimizations that you can do in hardware. And you'd never, ever buy a processor that didn't have a store buffer. Nobody would ever pay money for that anymore these days. So let's execute this in order according to the compiler. So processor 1 sets flag 1. So because that's a write, that write gets sent to the store buffer because we're buffering writes, right? This is okay because it's going to then get flushed asynchronously to memory, but by storing it to the store buffer, the processor can immediately keep going with doing other work instead of waiting for it to flush out to memory, which could take a while. At the very same time, on processor 2, we set flag 2 to 1. Same deal, it goes to the store buffer, and the processor can immediately continue executing while that's flushing to main memory. And you know what happens next? They both execute their next lines. Those are reads. There's no read buffer. Goes directly to main memory. They see the old values of each other's flags because it was just right in that little timing window, a nanosecond before the store buffer flushed, but it's too late, and it is exactly as if you had reordered those 2 lines of source code on each processor. Do you see what I mean? It's exactly as if you had reordered them and done the read before the write. Now, you might say, well, isn't that stupid? I wrote something. Let's go back a bit. I wrote a value to the buffer, and then I read. Shouldn't I read from the store buffer? Yes, you would if you were reading the same memory location. You're reading a different variable. The compiler, the processor, the cache system has no idea that this random memory location and this random memory location, which just have bit pattern addresses, have anything to do logically with each other. If you had written something to flag 1 and read it again, we'd read it back out of the store buffer because that would be consistent. But because it's an unrelated read, so we call this kind of example IRIW, independent reads of independent writes, because you're writing to two different variables. The compiler of the system has no idea what is the information that is only in your head, that flag 1 and flag 2 have anything to do with each other. They don't know how you're using them. And then you get the effect that it's as if you had reordered those 2 lines, even though this entire system from top to bottom is sequentially consistent, except only for the store buffer. That's an example also of, first of all, that there's just no hope. It's going to happen. Reordering is going to happen. Second, it can happen at any level. And third, they're all the same. A reordering at any level can be talked about as a source code reordering, which is useful because at least we can talk about them. So from now on, I'm only going to talk about source code reorderings. Question? I said processor 1 and processor 2. Clearly, they have two pieces of work running there. They have to be two threads of execution. So there's a thread that happens to be running on this processor and a thread that happens to be running on this processor. They could be two cores, but I'm just pointing out that they can actually be really concurrently executing in hardware. And then you get this kind of delicious cache effect. So from now on, we're going to talk about reorderings just at the source code level. There could be all sorts of mysterious reasons that reorderings happen, but we'll just talk about them from now on in source code. So now let's talk about optimizations, because your compiler optimizes things for you. And when I say compiler, I also mean your processor and your cache, but we're familiar with compilers. So let's just talk about simple optimizations we're all used to. So single-threaded optimization, just to start getting our feet wet. It is legal to transform x equals 1, y equals universe, x equals 2, to y equals universe, x equals 2. We're eliminating the right x equals 1. Why is that a legitimate single-threaded optimization? Christopher? Because you never read from x in between, right? And therefore? It's not visible. So both of these end up having the same observable results, right? So we've got basically a dead right that's never observed, so we can get rid of it. Okay, all right, now we're getting going. Let's try another example. I have a loop for I equals 0, I less than max plus plus I, the good old-fashioned C way, z plus equals a sub I. I would like to transform that to, instead of accessing the variable z, which could be a memory variable, every single time, I want to unregister that variable. So I don't want to reach to memory in a tight loop all this time. So I want to load z into a local variable, say a register. We usually call local variables R1, R2, and so forth, just because you can think of them like registers. I'm going to load z. Then I'm going to do the same loop, but I'm going to update the register. And then at the end, I write to z. By the way, this is a very important optimization. Compilers do this all the time. It's one of the very first thing a compiler optimizer will implement in his optimizer, because this is incredibly useful for reducing traffic to memory. Because you would hope that the cache system would do this for you automatically, even if your compiler didn't. You pull something in, update it, and let go. First of all, is this, as I claim, a legal optimization, and why? Observable effect is the same. So in a single-threaded program, the left-hand side and the right-hand side give you the same answer, right? So this is perfectly legitimate, and this happens all the time. Probably at least 30 years ago, the last time you saw a compiler that didn't do both of these. Now let's look at doing some more work. These could be char stars, they could be strings. X equals life, y equals universe, and z equals everything. I can transform that to z equals everything, y equals universe, x equals life, right? As long as these aren't class types with assignment operators that have global side effects, in which case I can't do it, but let's not get pathological, although it's what we love to do. I bet you I can find a case where this is illegal. If it is, the compiler won't do it. If these are just plain char star or string assignments, we could reorder these. By the way, why might we do that? Well, it might be that we just touched z a second ago, and it's already in registers. Before we spill registers, let's just do some more stuff to z first before we spill it and then load x and y, right? There could be very valid reasons to do this. And the compiler is doing you a favor, because you may not know from a reading of your source code that some function you called just worked on z. Therefore, it's doing something for you that you can't easily tell yourself. Right? So this is the reason we allow compilers to play these tricks for us, not on us. That we're coming to that. Now here's a fun one, another one you really want your compiler to do for you. I'm going to say for I equals 0 to rows, for j equals 0 to calls, -1. And I'm going to do something with this two-dimensional array and say add 42, because that is the answer, to every location in the array. Why is it legal to transform this to have the inner loop become the outer? to traverse the array in the opposite order? Because? Really, all we're doing is we're reordering the order in which we add 42 to the elements of the array. We're just doing them in a different order. Why is this one much nicer? Yes, so you're doing nice linear access order. Try both of those sometime under /od and enjoy. Do a little performance test. So that gives us just a sense of some optimizations that compilers are allowed to do and sort of why we think this is a good idea. The compiler knows all the memory operations in this thread because it can see the code. It can see right here what it's doing. That's its job, including data dependencies. So if for some reason X and Y and Z in the previous slide those assignments had side effects because they were overloaded assignment operators, compiler knows all that. And then it can say, okay, I know it's not safe if it isn't, because it knows what this thread is doing. Remember, compilers compile threads in isolation. That's a good way to think about it. They also know about aliasing. You have 2 pointers. They know you can play the dirty trick of sometimes having them point to the same object, and so they can back off and be conservative when they can't prove that 2 pointers don't point to the same object. And all of these put constraints on the optimizations they may do in order that the fiction remains true, that you get the same answer and you can't tell that we didn't actually execute the program you wrote. We executed a different program that is faster, but we can prove gives the same answer. Therefore, you can't tell. What the compiler does not know is which memory locations are shared variables that might be having reads and writes on some other thread it does not know about nor control the timing of. If you have an ordinary variable, you had better synchronize access to it because the system cannot do it for you. It has no idea if it's even shared, and even if it can prove that it's shared, what the sharing semantics are intended to be in your program. So it can't be conservative enough. So the solution is, tell it, this is why we use mutexes. This is why we use atomics. Think of it this way. We say to synchronize the program, yes, but more fundamentally, to tell the compiler, to express the information it needs to know about operations on shared variables across threads. Because that's the one thing that the compiler doesn't know about. It knows about all the local variables. It knows what this thread is doing. It does not know what other threads are doing. So we want to identify the operations on these mutable shared locations. So here's a fact of life from Java and now C++ and C. Software memory models have converged on the memory model that we present to you, the programmer, in a nice gift wrap package, sequential consistency as long as you don't write a race. So as long as you don't write a race condition, which means same object, 2 threads, and one's a writer, it's not synchronized well, as long as you don't do that, you get to pretend and maintain the illusion that we execute some interleaving of your source code threads, as if atomic access is to a single global memory, and it is merely hard to reason about. It's not impossible to reason about. Java has required this since 2005, C++ and C since 2011. But where Java says that this is the only mode of operation since Java 5, C++ and C say it's the default mode of operation, and it remains true unless you used relaxed atomics, which we'll come to. So the memory model is a contract. You guarantee not to write a race, and we guarantee that you can't tell that we didn't execute the program you wrote, because it will have the same answer. Here's a useful tool, at least I found it useful, and others have too, as to how to think about what a race condition is. Because when there's a race condition, how many of you have enjoyed seeing a race condition and seeing all sorts of weird stuff that was impossible? Okay. Forget about concurrency for 30 seconds. How many of you have enjoyed debugging an optimized build? Yeah, it sounds like someone did it on a weekend most recently. Yeah, Saturday night when there's a party and you can't go because it's just no fun. Tell me about some of the things you see when debugging an optimized build. What kinds of weird stuff that's probably illegal have you seen? Non-sequential jumps. So you hit step next, and you go up. Or, better yet, you hit step next, and your current line disappears. You're nowhere. How many have enjoyed seeing that? Okay. Yeah, disassembly, yeah, maybe. And even that's not always the truth because of what the processor is doing. So, yeah, isn't it strange when even disassembly is not the truth? We'll come back to that. How many of you have stepped over an assignment, say x equals 7, and in your locals watch window seen x change and some other variable change? So why can that happen? Well, if the compiler decides that you have two local variables, and after reordering, you only use the first variable x in this half of your program, and you only use variable y, local variable y, in this half of the function, and the variable y in this half of the function, after reordering, it could decide to save memory and store them in the same location, which means that when you step over, you assign x equals 7, you'll also see the value of y change, but it's okay because you haven't got there yet, well, at least not in the final program that we're executing. Why do you get to see this? The program that you run, as long as it doesn't have bugs, gives the same result either way. It's only if you're in a debugger that you can see these pink elephants. What does this have to do with race conditions? If you write a race condition, one thread can see into another thread with the same view as a debugger. This is flatly true. Anything that you could see in your debugger seat, pink elephants that even you don't understand without a lot of analysis, your thread is going to be helpless when it sees a race. This is why the memory model is, if you write a race, you go straight to undefined behavior land. Have a nice day. Because your program can't possibly cope with all this weird stuff that you might see. And we've just scratched the surface of the kinds of things you see in an optimized build. You can see torn writes. You can see partly constructed objects, partly destroyed objects. There's all sorts of stuff that we just really never want to try to deal with. But this is a good parallel to think about what data races are like. So now let's talk about what acquire and release orderings do. First, the key concept is of a transaction. A transaction says if I take the system from one valid state to another, it better be atomic, take the system from one consistent state to another, be independent, so if I have two transactions, they don't conflict. An example is, let's say I have two bank account objects, and I credit 100 to one, and I debit 100 to another. Somehow, I want to wrap that in a transaction so some other part of the system does not see the total of money in the system be an invalid value, where temporarily I see $100 extra in the system that then ephemerally disappear. So I want this to be a transaction somehow. The way we do this is we express the critical region as a critical region start and end to delineate what the transactions are. And the way we do this for concurrent code is with our common tools. If we have a mutex, then we can take a lock on the mutex, read and write whatever is protected, and release the lock. So acquire the lock is to acquire exclusivity. Release the lock is to release exclusivity. We use those similar words with a mutex. We acquire a mutex, a lock. We release a mutex lock. Anything you can do with mutexes, you can do with atomics, because you can easily write your own spin locks using atomics. Look, here we're doing it. You'd usually never write this code except under very low contention, but here's a spin lock implementation with atomics. If whose turn is an ordered atomic, we spin on, as long as the value isn't me, as long as it isn't my turn, so somebody's going to store a thread ID, somebody else whose turn it is going to store my thread ID there to tell me it's my turn. We spin until it's true. Now I've acquired exclusivity because I have acquired that value that says it's my turn. I then do my things, and then I release exclusivity by passing the baton to somebody else, by doing a write to the atomic variable to say now it's somebody else's turn. This is very important because an atomic read, or a read modify write like a compare and swap, but an atomic read logically is an acquire operation. Atomic write or store is a release operation, because that's what I use to publish the new state to somebody else and say it's your turn now. And even if someday we get transactional memory, which would be nice, the same thing applies. We just spelled a different way. Atomic region begin and end is critical section begin and end. The key to all of this is these are not different concepts. These are the same concept using just expressed through different tools. So it should be no surprise that they actually end up generating much the same code. Now, but let's talk about what some key rules are for critical regions. Let's say I've got one expressed through mutexes. That's easy to talk about. So I lock a mutex. I say x equals 42. I unlock the mutex. Is it legal for a compiler, processor, cache system to move the x equals 42 write up over the lock acquire? No, because it's red. And because this is exactly the situation that Scott was showing in his slide. I'd be injecting a race condition. Because some other thread that is correctly doing the lock, use x, unlock, but happens to be reading from x, even if it's just innocuously reading, is now going to race with that write, and they could possibly see a torn write, say some of the bits written, some of the bits not, or other weird things, even just for an integer, much less if you have several variables, okay? What about moving it past the unlock? Same thing. So think of it this way. Moving code out of a transaction is unsafe because you're moving it from a protected region to a less protected region. If the programmer said, here's a protected region, it's always safe to move code in, but not out. So in, what if I have a mutex lock and an unlock? Inside the critical region, I have y equals universe. So this one starts out as being protected by the mutex. So presumably, the mutex protects y, say. And some other possibly local variables I have before that, x and z, I'm modifying before and after the transaction. It is legal to move them into the transaction. In fact, I can move z equals everything up across this release. I can move it as high as just under the acquire. And conversely, I can move x equals life down across the acquire as far as just before the release. Because conceptually, you can always take something from a less protected region to a more protected region, and that can't cause a bug. It could cause performance issue. I mean, you don't want to hold locks longer than necessary, so usually you wouldn't do this kind of thing, but it's legal, and it's important to know it's legal. Sometimes it is a benefit if you can coalesce work. But you cannot take the next step of then saying, let's reorder it further so that the z equals everything floats up even higher the wrong way across an acquire, and the x equals life goes out of the critical section. Now you might say, well, wait a minute, I can see, forget the left side. If you'd started with a middle code, clearly you couldn't do this by what we just said on the last slide because you can't move stuff out of a critical region, right? But people are tempted to reason, yeah, but I happen to know that work didn't even originally start in the critical region. So maybe it's safe to just move it through. Since it really wasn't part of the critical region, I know the lock isn't protecting it, maybe this should be allowed. I'm not going to dwell on it, but the short answer to that is when you release something, what you are conceptually doing is you are releasing all actions taken by this thread so far, which include, in this case, mutex unlock, anything you did to the data protected by the mutex, but also any other work that you did. Imagine that seeing y equals universe is a flag which, when seen by another thread that acquires the lock and reads y equals universe, says, ah, this means that the original thread was done writing x. I'm going to use x now. It transfers ownership. It might mean that. Therefore, we had better not move the writes to x down below that, because otherwise we're not releasing the entire state of this thread that's doing the release operation, so that anybody else who now acquires exclusion is guaranteed to have seen everything this thread did. Conversely, if we floated the other up across, you'd get the opposite problem, same problem, but from the other side. I'd be doing things before the acquire, means I wouldn't necessarily see the state that I acquired from somebody else. So those are the reasons for the rules. You can always move code in, but not out. So you can't move up across an acquire or down through a release. These are one-way barriers. These are fundamental concepts in hardware and in software. And we're going to see how this plays nice all the way down to the hardware. So more precisely, a release store makes all its prior accesses visible to a thread performing an acquire load that pairs with that store. I release a mutex on one thread, another thread acquires that mutex. It's guaranteed, if it happens after, to see everything that thread did, and so on. Any questions about that so far? Start here. Yes. The question is, we saw in an earlier example that we write to the store buffer. Well, that's a hardware thing. Maybe this is only obeyed by the compiler. This is a fundamental hardware and software concept. What the compiler will do, as we'll see in a slide, it might even be the next one, any synchronization operations like atomic reads, write, mutex lock, unlock, generate special instructions that tell the hardware to play ball to. What you've done is in your source code, right up here in the stratosphere, in your source code, way up at the highest level, you have simply identified what the critical regions are, and we've given you a few tools as to how to do that. We then better obey that all the way down, so that the execution we end up with obeys all those cross-thread dependencies that the compiler and the cache don't know about. Because remember, they know about all the single-thread dependencies. They can optimize those to their heart's content. They're very good at that. They don't know about cross-thread shared variables. This is how we tell them about them. How does the compiler know that a function named lock is special? Exactly. Well, actually, it's throughout. So you'll probably, first of all, you'll see that these are often implemented using atomics. And so it will see that it's using special instructions through atomics, and the same things apply to loads and stores. We're going to see how that works. Now, what if this is an opaque function call? If the compiler encounters an opaque function call, let's say instead of calling mutex lock, we call function foobar, which internally happens to take a lock. Compiler can't know that. Therefore, unless the compiler can prove otherwise, it has to assume that any opaque function call is a full barrier, that you can't move anything across safely. So that's being conservative. If it can see the implementation, then it may know it's safe to move things one way, which gives you some more optimization. We'll come back to that. So good fences make for good neighbors. A cute barnyard scene there. Acquire and release are the two main barriers we're going to talk about, but we'll also sometimes see a full fence, which you should rarely need. Often that gets written for you if you do compare and swap operations and that kind of thing. You should rarely need and write directly, but it comes up in some of the examples, so I'm going to show it specifically with a graphic. Now, I mentioned there were two flavors of acquire and release that differ in a very tiny but important way. Plain ordinary acquire release operates on the rules I just said. You can't move anything up across an acquire or down across a release. Now think about what this means about acquire release pairs themselves. It means that I can't take an acquire release and move them past each other because they'd each be moving the wrong way. So this is all good so far. The one hole that, if all you say is you can't move up across an acquire or down across a release, the one hole this leaves in the story is that a release acquire can pass each other, and you don't want that. So the one extra rule we say is, in addition to you can't move code up across an acquire or down across a release, in addition to that, you can't reorder acquire release operations with each other at all. And the only thing that turns off is what we call the store load reordering, the release acquire reordering. So that one extra rule makes release acquire completely sequentially consistent. So if you're familiar with Itanium code generation, for example, you'll know they have the instruction load.acquire and store.release, and they do this, which is why you need the extra fence on the store that I'm going to show you. A more modern processor can implement these directly, and we'll come to that. So when I talk about sequentially consistent acquire release, I just mean that things stay in program order, including the acquires and releases themselves, just to close that one little hole. Imagine that each of these was a single thread. So in this thread, you see an acquire, then you do other stuff, then you see a release. How much can you move them around together? You can't move them across each other, but you can move them up to as close to each other as possible. If there's only other ordinary memory operations in between, you might be able to get them. Well, you can't move things out of the critical region, but if there's nothing else in between, they can go up to each other but not across, right? Whereas if it was the other way, like say this was a mutex unlock followed by a mutex lock, Clearly, you don't want to do this because, for instance, you might, if you implemented this yourself in a spin lock, you might now have 2 locks at the same time. This is bad. It could inject deadlock, because maybe your system, your program never should acquire those 2 locks at the same time. To close that hole, we just say, just don't reorder these to special instructions at all. It's ordinary memory operations you can move across acquires and release one direction each. Oh, because this is the end of the prior critical section, and this is the beginning of some other one that may be unrelated. Yeah. It's a fact of life that any synchronization you do, including this kind of memory synchronization and constraints, actively work against to try to defeat modern hardware optimization. So we try to do as little of this as possible to keep as much of our optimization as we can. Remember, we want to keep the memory pipeline full. The more bandwidth we have to memory, like any pipe, but the greater the latency, the more concurrency we have to have in the system. As this is a quick look at what processors do, processors inject all sorts of concurrency, from store buffers, caching, pipelining, out-of-order execution, just to keep the memory pipeline full, have lots of memory requests in flight. The more we interrupt that flow, the lower our performance will be, because we want to keep as much memory stuff in flight as possible. This is one of the reasons we reorder, is so we can launch memory operations sooner, so we can do other work while we wait for the pipeline to drain and come back. We don't want to interrupt this flow if we don't have to. And in fact, if you look at a sample modern processor, some of you may have seen this slide before, what's in the green lines is all the transistors that do only caching. If you think that that means that only 15%, because that's about 85%, that only 15% of the transistors on your chip actually calculate anything, that's way too high, because in the non-outlined part, you're also doing other kinds of memory hiding, like pipelining, out-of-order execution, speculation, all those things. So roughly 1% of the transistors on your chip ever actually compute anything. All the other 99% are there to hide memory latency, to keep this pipeline full. This is just to give you a flavor of they're working so hard for you, you really don't want to interrupt them doing this hard work unless we really have to. Now let's talk about how we express acquire and release. We don't want to write fences by hand if we can help it. I'll show you some examples, and then you'll appreciate that. We do want to make the compiler write the barriers on your behalf. The way you do that is by using locks and atomics. So we've seen these examples before. When I do a mutex lock, that's an acquire barrier. So I'm showing the little graphic there showing it's legal to move code down across the acquire barrier, but not up, because that would be moving it from a protected region to an unprotected one, right? And a mutex unlock is a release barrier. I can move things up but not down. So you can't move the code out of the critical region. If you look at the code that's generated for that, say on Itanium, you will see, among other things, a load acquire, or its equivalent, for this mutex lock, because the compiler recognizes this is a special operation. It obeys the synchronization, the acquire barrier, and it emits a special instruction, not an ordinary load, to make sure everybody downstream also remembers to obey that don't move stuff up across this. And Itanium happens to have a nice instruction for that called load acquire, and you will see it or its equivalent in this kind of situation if you look at the disassembly. On the release side, you will see a store release and usually a memory fence and stuff. This or its equivalent, you will see a store release instruction that tells the hardware, hey, I obeyed the rules. I didn't move stuff up across this release. Don't you either. And so everybody all the way down obeys the rules. If instead of mutexes, you wrote this with atomics, remember we saw this while it's not my turn spin, when I acquire, when I'm reading the variable and now it's my thread ID, so now I know it's my turn, because I'm loading a value and I see that the value is a certain value, that means I've acquired exclusivity. So a read of a certain value is I've acquired that value, I've acquired exclusivity. Guess what? Generates the same instructions. Same thing or the equivalent. There's usually a set of instructions in the processor. Whether I express it with a mutex lock or with an atomic read. When using atomics, I've finished my critical region, I release the next person. So I release, I say, I'm done. I now want to make everything I did visible to whoever comes next, and now it's your turn. I do an atomic store or a write to the atomic variable to say it's somebody else's turn. Guess what? That ends up generating the same instructions you see for a mutex unlock. So these are two different ways of expressing synchronization, but they use the same sets of hardware instructions. And for each of these, for mutex locks, you might see a different instruction pattern because it's actually doing different kinds of things, especially if there's backoff or other kinds of things. But they use the same families of synchronization instructions in the processor, and that's how we obey the rules all the way down. Did I see a hand before? So the question is, what if you have multiple atomic accesses in a row? Can you optimize the acquire releasedness? The answer is yes, sometimes. But it depends, especially if it's the same variable. That's easiest to do when it's the same variable. But often, the processor itself needs to pair a store release with the subsequent load acquire, which means you need that releasedness on each instruction. Because if you're, say, writing to X, then to Y, then to Z, X write had better be, if they're all atomics, had better still be a release so that it can pair up with another acquire of X in another thread, because these always come as a package deal. Acquire release come as a package deal. If I do a load acquire and I see a certain value, I guarantee that I pair up with a certain store release and see everything else that that thread, whoever did that store release, did. And so that's how the synchronization works under the covers. So how does the compiler know that these are special instructions? And you can ask the same question about atomics, by the way, because all I'm doing is an atomic atomic load, so a read. It's because they're implemented using intrinsics or a special compiler, a special inline ASM or something like that, eventually down under the covers. Usually you see intrinsics. On Windows, you may see special function calls like interlocked increment and that kind of thing. All of these are somehow known to the compiler as special instructions. If you want to write your own special instructions, you can special functions, you can build them on these. You can build a function that uses atomics internally, and everybody knows what's going on.
I guess my question was more like,
Okay, so if you write a function that uses that intrinsic, and then it gets called by somebody who gets called by somebody who gets called by somebody, because it may be way down in the call tree, does it, I like the term you use, does it infect all the others? It remains a barrier. Yes. Infect. Infect sounds so viral. Any other questions about this? So I did not actually say it flushes the entire store buffer, but that is a valid implementation. It's you want to at least flush the store buffer usually. You may also want to do other cache synchronization, because the store buffer flush only gets it to L1 usually. You want to get it all the way to main memory and invalidate other people's caches so that they see the correct things. This can be a very heavyweight synchronization operation, unless you can be more fine-grained about which things that you're actually synchronizing. We'll see some examples. One more, and then we'll continue. So what if, okay, so in this critical section, I've got a read of a special value, I acquire exclusivity, then I have a right to release it to the next guy. You're saying, well, what if you don't have the right? Well, that just means that the critical section never ends, or it's the last one of the program or of the thread. So you're looking for like a stop flag being set. That just means you're saying, okay, I've now, conceptually, you can say I've acquired, I'm in this new stage, but that's the rest of the program for me. So there may not be a next release there, because you're not releasing it for somebody else now. You want to release when somebody else is going to pick up the baton, acquire the mutex, or acquire exclusivity on whose turn to do more stuff. And then you'd better release it, otherwise, if you don't write this release or this one, that person will never get a chance to run. So you do the release when it's now going to be somebody else's turn. So now let's talk about how sequential consistency is more than just about acquire release. And I'm now going to get into things that you do not need to know, but to give you a sense of that, no, really honestly, we really try hard to play by the rules, so that if all you tell me is the acquire release parts, that we make our lies okay. We make our lies invisible, that we're not executing the program you wrote. In addition to obeying, don't move stuff the wrong way across an acquire or release, here are some other things, just so you understand how hard people are working to maintain the illusion that we're actually executing your program. We would never do that, but that we're actually executing your program. Consider, this is one of the examples that was used a lot in the memory model discussions that we had during the late 2000s. Say thread 1, okay, first of all, x and y are atomic variables, and g is just some random global variable. It's not atomic. But they're all initially 0. So thread 1 sets g equals 1. Thread 2, and then sets x equals 1. Here, let me try something brand new that I've never tried before, which is always dangerous. So thread 1 sets g equals 1 and x equals 1. Once it's set x equals 1, it's done. Thread 2 says if x equals 1, then it's going to set y equals 1. If thread 2 runs after thread 1, then this will be true, right? And it'll set y equals 1. And finally, if thread 3 runs after thread 2, it's going to see is y equals 1. Then it is going to assert that g is also 1. Now, logically, this had better be true, right? Because from a sequentially consistent reasoning, if I reason only about source code order, if I, in thread 3, see y equals 1, that means I know that thread 2 got to that right. Which means I could reason, and this is the reasoning we have to make sure we don't break, I can reason that therefore it must have tested x and seen it to be 1. Therefore, I can reason that thread 1, who's the only guy who set x to 1, has reached that far, which means he has also set the value of g. See what I mean? This had better be true. If for some reason this were not true, and we synchronized only the atomic variables, say, this would be completely broken. We would have violated causality. We would have no longer been able to reason about our program in a causal way. And think about what this means. If thread 1 does some ordinary write and then sets x equals 1, x is this atomic variable, remember that's a release operation. It's releasing all the work that that thread has done before it wrote that, including g equals 1. So whoever sees that x equals 1 had better also see the g equals 1. And then whoever sees x equals 1 and sets y equals 1 and so forth, who sees y equals 1 must see everything. It must all come along for the ride. So that's one example that has to work. Here's another one. Imagine that you have two threads. We set x equals 1 and we set y equals 1. So thread 1 sets x equals 1, thread 2 sets y equals 1. Thread 3 says, is x equal to 1 and y equals to 0? What does that mean? It means this thread ran already. Thread 1 ran before thread 3, but thread 2 didn't yet. So our ordering is 1, 3, 2. So it can say, x was written first, because I can say thread 1 ran before thread 3 ran before thread 2, therefore, thread 1 ran before thread 2, right? It had better not be possible for some other thread 4 to come along and observe the opposite. So even though thread 1 and thread 2 are setting independent variables, there better be some total order so that everybody agrees on who came first. Because if I could see y equals 1 and x equals 0 here, then I would think that thread 2 ran first. And now I no longer have a causally consistent system. I can't reason about this. There is no way you can write correct code if this isn't true. So that's one example of how we need to make sure that we keep things true. Now let's talk about using mutexes. The advantage of using mutexes is that they induce this ordering, and you nearly never have to think about this stuff. Because you just tell us, here's the mutex lock, here's the mutex unlock, and we just make it all true because we know all these rules. We don't move things the wrong way, and we keep the causality correct, and everything's good. And that doesn't mean you have to, every time you use a shared variable, you have to take the mutex lock and do it correctly. And there's a whole talk about how to do that correctly without deadlocks and lock hierarchies, but it's merely hard, right? It merely requires attention. You can also use atomics. Special atomic types, like we saw, are free from these reordering issues. So in Decker's algorithm, if you had written flag 1 and flag 2 to be atomic int, or atomic bool, then that would have guaranteed that these reads and writes would not be reordered. Even though it was a store followed by a load, remember pure acquire release would have allowed you to reorder this, but sequentially consistent acquire release turns off that one reordering also. And Decker's algorithm will work if you make the flag variables be atomics. The nice part about this is you can just tag the variable once, not every place it's used. So you just say the variable is atomic, and then every place you use it, your program just runs in the order it appears to run it, that the source code appears to say. The disadvantage is using atomics is much harder than it seems. How many of you have had the pleasure of writing code using atomics? How many of you would characterize it as easy? Good. So, in fact, one data point I'd like to show is if you usually use this to do lock-free or low-lock kinds of coding, some common data structures, like a doubly linked list, last time I looked, which was about 3 years ago, had no known practical lock-free implementation. There were some impractical ones. I've heard a rumor that there is a possibly practical one that has come along. I haven't seen it yet. But that gives you a sense of just how hard this is to do. Even a singly linked list is very difficult to do because everything is easy, relatively, except the erase a node, because it's hard to know when it's safe to erase when you're being fluidly lock-free. That said, you can use atomics in a lock-like way. If you spin it on atomic, that's much like a mutex lock. You just implemented it yourself as a spin lock. But you have to know what you're doing here. The way you spell ordered atomic variables is in Java and .NET, you call them volatile, and they're always SC. They're always sequentially consistent. Now, in .NET, that's mostly true. Decker's algorithm is broken on .NET volatiles, but almost everything else will work because they're just acquire release. They're not full SC acquire release. So .NET's almost there. Java's fully there. C++11 and C11 atomics are fully sequentially consistent by default, not all the time. If you reach into the memory order underscore bucket and you say, I want to explicitly take over saying what the memory orders are, then, as we'll see, you deserve what you get. But at least on x86, there's a performance reason to do it on Power and on ARM today. But by default, they're sequentially consistent. And what you get are that each individual read and write of an atomic variable is guaranteed to be all or nothing. They are guaranteed to be executed in order, in source code order. And you get a couple of extra instructions, the functions on them. Exchange and compare exchange, which operate roughly as this source code shows, except that they're not written in this source code. They're an atomic execution of the equivalent of this source code. Usually, there are processor instructions like compare exchange that directly implement them as single atomic indivisible instructions, which also can't be reordered. So in C++11, the compare and swap is spelled compare exchange strong or compare exchange weak. The way you use this is you might say if my atomic value dot compare exchange strong from expected to desired. If it atomically says, is it the value expected? If yes, atomically also set it to the desired value and return true. I changed it. Otherwise, return false. That's the same as I showed here. If this value is expected, then we set it to desired and return true. Otherwise, we're going to actually going to tell you what the old value was and return false. And the way that you think about this, compare exchange strong, if val compare exchange strong from expected to desired, it's pronounced, am I the one who gets to change val from expected to desired? And it's often written in a loop so that when you use the strong version, you're usually doing a single test like that if. Prefer the weak version if you were going to write a loop anyway. The difference is that the loop is allowed to fail spuriously. What that means is that even if the value was expected, I may just, for other reasons, like I don't like the look of you this nanosecond, say, no, I failed. That's OK if you're going to be doing this test in a loop anyway. But if you're going to be doing it as a single test, you really just want to look once and you want to know, not have a spurious failure, then use the strong version. The reason the weak version is that there can be extra efficiency sometimes in doing that if you allow the possibility of spurious failure. And you don't care about that if you're testing it in a loop anyway. The third way that you can inject memory ordering is to write fences. How many of you have enjoyed writing fences yourselves? I'm going to guess probably quite a few. Oh, not as many. OK, that's interesting. So I'll show Linux memory barriers and Windows memory barriers. On Linux, you can write a full MB, which is a full memory barrier. And on Windows, you might say something like interlocked exchange. What this does is it takes flag 1 and flag 2, those two, the store and the load, and it injects a barrier in between that says, do not reorder anything across here. Specifically, it means I can't reorder the read and write of flag 1 and flag 2, which saves me, because that's what I need for this algorithm, Decker's algorithm, to work. On the Windows side, I can just say interlocked exchange flag 1, 1. So I'm using a special instruction to actually set the flag. So this is not so much a fence as a special ordered API. And because it acts as a full fence, I can't move the read of flag 2 above it. So again, things stay in the right order. The disadvantages of fences and writing these special instructions is they're different on every different processor, and also in the interlocked exchange API case, they're different on every operating system. They're tedious. You have to know what each of them are and write the right one in the right place every time you use the shared variable. They're error-prone and hard to reason about, so when you see papers on lock-free algorithms, they usually don't say where the fences go. Very few even try to say where the fences go, because it varies so much by architecture and because it's so hard. And these fences are usually, often, too heavy, because you end up resorting to full fences most of the time, because that's the main thing you can actually successfully reason about. And remember, we said most of the time we want acquire release. A full fence says stop everything. Nothing moves up, nothing moves down. Acquire and release are much nicer. They say, well, you can't move that way, but you can move this way. And so it imposes a stricter ordering than you actually need much of the time. So let's consider an example. Let's say I have thread 1, and here on thread 1, I allocate and construct a new widget. I assign it to a local temp variable, widget star temp equals new widget. Then I set a global variable. This global is atomic, and I set it to the value of temp. So that's a release operation. On thread 2, I'll read the global variable, and assuming that it's not null, so if that thread runs before this one, it's just set to some other widget. I run global arrow do something, global arrow do something else. What kind of synchronization do I need here for this to be true? By the way, I said global is an atomic variable. This question would be moot if it was, so let me take that back. Assume that global is not an atomic variable. What synchronization do I need here? So you somehow need to release this and acquire here. And how do I do that? So I could put a lock around the global. So lock, write to the global, unlock, and over there, lock, read from the global, unlock. OK. What if I wrote fences? What fences would I need? You need a release over here and acquire over here. Do you need an acquire before each read? Because if that were an atomic, you'd be getting an acquire operation on each read of global, because you've noticed there are 2 reads of global in thread 2. So you need release and acquire semantics, but what are the rules? How would you write this with standalone fences? Imagine that you inserted a full memory barrier in thread 1 before the write to global. This guarantees you what? If I write this full barrier here, this guarantees you what? Nothing moves either way. So in particular, by the time I write temp to global, all of the other operations will have been seen to occur that I did in this thread. OK. And over here, I simply inject the fence after the read from global to make sure that everything I do with the result of global stays down below. And let's just say naively, since there's 2 loads of global, I'll just do the same thing in each one. And we could collapse that also, which I'll show. What are the usability and performance issues of this? First of all, are full fences even necessary? What are the performance issues? Is the code correct? Is it usable? So you got some memory performance overhead because you're requiring a full synchronization here with a full barrier. True. So do you need a full barrier? Because we've just been talking about this whole acquire release thing. Seems like you should just need an acquire release here somewhere, right? Do you need a full barrier? Yes or no? Let me rephrase the question. Why do you need a full barrier here? Because of code I'm not showing you. Yes? Yeah, so if this memory barrier were just one way, then, for instance, say the memory barrier itself was a release, notice it's not associated with the store to global. It is a standalone memory barrier. Therefore, things can flow which way across it? Up, which means the write to global equal temp can skip right over and then get all the codes together again. Now the fox is in the hen house and mayhem ensues, right? So that wasn't enough. Another reason it's not enough is imagine that there was some global variable, some other side effect you were going to have. So some other global variable you're going to write g equals 1. And let's say in thread 1, so before we do this, does everybody agree that yes, we need the full fence here, and the reason is because this ordering is not associated with the store to global. It's because it's a standalone barrier which loses information. I haven't associated it with the thing that I actually would like to express it on. Therefore, it has to be a full barrier, otherwise things can move across, and I lose all the benefit, right? Question about that? Yes, because as opposed to acquire release. Because imagine that full barrier here, imagine that was a release barrier. Now not associated with, it's a standalone barrier, not associated with a load or a store, but let's say it was just a standalone release barrier. Do not move anything down across me, right? I can still move things up across it, including the store to global, and now I'm in a mess because I've moved it across and up. Now it's together with the widget construction and allocation, and I can do things out of order, see partly constructed objects and things like that again, because I could store to global before I finish all the writes to constructing the widget. So it doesn't do enough. Because it's standalone, it's not basically release makes no sense on a standalone fence, because you're saying don't move anything across this variable load. You got to identify what the variable is. Otherwise, you can just move things one direction and they're all together again. It doesn't have any effect. Now, there's another performance issue. So now that we've seen that, and the same reasoning applies on this side, we need a full fence. And the reason we need a full fence, again, is because it's not associated with the store to global. If it was global was an atomic, it would be a store release and everything would be fine. There are other overheads. There are other pessimizations we've opted into here. If we have this other work we're doing, say that we have a global variable, g equals 1 in thread 1, then I do the widget construction, the barrier, the assignment to global, then I say x equals g, say, just for some reason. I do some other work. Over here in this thread, I have some other variable y. I set y equals 1. I do my work with my barriers, and I say y equals g. Now, thread 1 sets g equals 1, right? Then I have the barrier. If here I acquire, well, there's no acquire, but conceptually, if I acquire the value of global that was set by thread 1, what had better be the contents of y? I better have the y equals 1 because we set the g there, right? I better have that because I need that transitivity. I get that because I globally synchronize the world all over the place. But it means that I need this fence because the G might exist. Data dependency isn't enough because that memory barrier, that assignment to global, might also be publishing the value of G to be communicated across here. That's another side effect of what it did, just like the writes to in the construction of widget. And I mean, I can't do constant propagation here. I can't, for example, do a normal single-threaded optimization of changing this code to x equals 1, which I could basically now initialize this much more easily. Because I see g equals 1, therefore x equals 1, no, but no, I can't propagate that down. Something else might have happened in between. Therefore, even the intra-thread optimizations are disabled because I can't be conceptually moving that right down, which is what that would mean. On this side, I can't eliminate this redundant right to y. So I have no idea if it's a shared variable or not. I have no idea if the other thread is going to look at it. It isn't, but I don't know that. So even though I see y equals 1 followed by y equals g, and I see my thread doesn't look at y, I can't eliminate that because the programmer might be reasoning about his code and using that variable in some other place. Further, because I have this second fence in here right now, I can't even optimize these two function calls if they have common code, which they might have since they're member functions of the same type. So you can see where these barriers, in addition to creating these sandbars in my memory order pipeline, they're also inhibiting more than maybe we expected of even single-threaded optimizations, because we say, don't you cross here, don't you cross here, which means we synchronize the world and we prevent the reordering even within a thread. So the question began with, yes, standalone memory barriers, pessimize, bad thing, avoid them if you can. Of course, you may not have atomics yet, but if you do, avoid these. But then you said, what about talking to hardware, like, say, memory mapped registers or memory mapped data, something like that? That's at the end if we get to it. So see the section on volatile at the end. The short answer is the tool you want there is volatile, has nothing to do with memory barriers. Oh, and you're next, I promised. So I've inserted a memory barrier here before global is initialized. I'm assuming global has been initialized somewhere else. It's got some other value. Say it's pointing to some other widget. And now here, he's creating a new widget and pointing it to this one instead. So this code, if it runs before that thread, is going to just do the operation on the previous widget. If it runs after that thread, it'll do it on the new widget. Because we're reading global twice in this case, it might do this operation on the old one and this on the new one. Which, if we merge those, now we can remove that, where it's either going to do both operations on the old widget or the new widget. And that means if we do this, by the way, that means now we can get rid of that third problem. We can optimize these two function calls as normal if they have common code or things like that. But all the other problems remain, and these are just illustrative. The question is, ignoring the barriers, you're saying if global was an atomic, could we do the constant propagation? The answer is yes, because we couldn't move the g equals 1 line down. And conceptually, you're saying, oh, look, we're moving the 1 down. But we can move the x equals g line up. And we just needed to move it up 1 line, and now it's in range. Now we can do the constant propagation. Fun stuff, huh? If y is a local variable, the same reasoning applies. Oh, but if y is a simple local variable or a thread local storage variable is the same thing from thread 2's point of view, right? Because y is, as we're using it here, we happen to know it's only being used by thread 2. But the optimizations are pessimized because the compiler doesn't know that. You might mention y over here, and if you don't today, you might tomorrow. And so because it doesn't know that, it has to be conservative. A store to an atomic is a release operation. It's only a release. And the key point here, yeah, no, that's perfect, because this is the kind of thing that, I mean, I had no idea what a memory model was. I managed to get through my entire career until about 2006 and never know what a memory model was. And then you should be afraid, participate in designing one. So we don't even want to know this stuff, and we can get away from it. So it requires many repetitions. So do not be afraid to say, was it an acquire, was it a release, was it both? Because it takes a while to get used to these things. Load, acquire, store, release are the primary things. So when I store, I get just the release semantics and the one-way fencing. The key point here is, hey, look, If I don't associate it with a variable and I try to write a standalone fence, I very quickly resort to full fences and I pessimize in various directions. One more question and then we'll continue. Is there any chance that when thread 2 is reading global, it could see a torn value of global? I am assuming for simplicity that the only issue here is ordering, and that global on your particular platform and compiler is a properly aligned and actually in hardware, atomic, indivisibly readable and writable variable. You should be so lucky. So an aligned int on x86, for example. But very good question. I should have mentioned that. Right. So, but the key, there's an interesting key aside to that. Even on x86 with a properly aligned int, a very frequent question is, well, I don't need it to be an atomic because I know it's atomic. Yeah, but that's only half the story. The other half is ordering. And you desperately need the ordering guarantees, which is what we're talking about with the fencing here. Remember, atomics give you two guarantees, atomicity, indivisible, reads and writes, even for atomic of big, huge pod. We support that, for better or worse. It works. And for the memory ordering. And it's that second one that we're focusing on here that the barriers give you. We assume you get atomicity some other way. Yes, you're playing with razor blades. Isn't it fun? Let's take a break, and we'll come back in 20 minutes. We're a few minutes before break time, so we'll start a few minutes before 11 o'clock. And then we'll talk about other restrictions on compilers and hardware and get into actual code gen.